I'm Zach Russin. I'm an engineer working for VMware. Most of you probably doesn't know, but I'm actually a mentalist. So I'm not sure why people are laughing. But by looking at the faces, I can tell that what everyone is thinking, and I think the burning question on top of everyone's mind right now is, will Lakers repeat? Obviously, with the loss of Trevor Ariza and with Ron Artest now on the team, I think it might be a little difficult. So I think right now there's not a doubt that I can read your mind. So I'll be able to spend a lot of time talking about basketball, unless of course there will be questions pertaining to the actual presentation. We haven't seen almost any questions, and I'm really buying into this whole philosophy of there not being stupid questions. In fact, we're going to do a demo. Michelle, can you ask me a question? No. Question? Too much pressure. Oh. Wow, you. Yeah. Excuse me? Excellent. Thank you very much, Susie. There. So it's pretty easy, and I think it's going to be a lot easier for everyone if you just stop me and ask me questions. I know John had some questions about OpenVG. We're going to get to OpenG later, but if there's anything that's unclear, or if I'm being unclear, or if I'm talking too fast, just stop me and let me know. So this is a very short presentation, basically giving you a background of what state trackers are, how do they work, why do we have them, and how to easily implement one. First of all, the reasons for state trackers. I think they should be pretty obvious by now. It's the fact that complexity of hardware and APIs that we're implementing on top of the hardware is growing almost exponentially. The complexity of all the APIs that we're implementing on top of GPUs now is really coming down to the complexity of the programmable pipeline and shading languages, but because of the wonky semantics of memory handling, there's a lot that has to be done in the driver just to support a given set of chips, and APIs are not making it easy. And combining the set of APIs, high-level APIs, with the low-level device driver code is a recipe for disaster. It's started getting to the point where it was almost impossible. And surely a lot of you who have implemented drivers know that mixing of APIs and device drivers makes deployment a lot more difficult, because besides copy and paste that is happening between drivers, there's a lot of Q&A that has to happen for pretty much every single API that you support with every single GPU, and all of those drivers share different parts of code, and that makes it almost impossible to deliver on time. And we looked at all those problems and try to find a solution or make it a lot easier for us to actually provide drivers with new APIs and decouple the APIs from the hardware drivers. And initially, if you know MESA stack, it's supporting GL, and it's basically everything is in the driver. And you look at this huge code base, and you get to a point. Oh, bummer, man. So anyway, what the picture is supposed to portray, which unfortunately it does in two variations, is that at some point you need to give up. There are cases where it's really hopeless, and you need to start from scratch. And this is what the state trackers were. It's basically a way of putting API on top of the Gallium interface. So there's the Gallium interface, which is a very thin interface, as Keith already established. And on top of it, we put the entire state-related functionality for any given API. And I think what hasn't been mentioned is that the entire complexity of the Gallium stack is supposed to be encapsulated in the state trackers. So the Gallium hardware driver, the Gallium interface, and everything that is device specific should be as simple as possible. The complexity of the entire stack should be encapsulated in state trackers. The reason being that state trackers can be shared. They can be shared between drivers, and they can be shared between operating systems depending on the winces that you're using. So a lot of the peculiar functions of the given APIs is completely hidden from us, and it resides in the state trackers. And because of the Gallium interface, we can share any API with any hardware driver and any winces. So OSs and different GPUs don't matter to us as long as we use the Gallium interface. And that was really the fundamental decision that is leading the Gallium development. All the state trackers do a little bit more work than would be probably required if you implemented them right in hardware, but it allows us to more rapidly change our client-side code without actually affecting the drivers. So why do we have state trackers, and what do they exactly do? It's really the implementation of any given API on top of the Gallium interface. And I guess what makes it so unique is that the Gallium interface is so thin that it's really easy to create something very quickly that at least does the basics, and it's very easy to bootstrap that whole process, and allows you to completely decouple hardware developments from the API development. So the teams who actually deal with graphics development can be split into the teams that support purely API, be it GL, DirectVD, OpenVG, or whatever, and the guys who actually deal with device driver development. So people who get the specs and nail down the driver as it happens, and as soon as they do it, they can just put it in, and the API will be used automatically. And the evolution of the API is not coupled anymore to the driver. So it's perfectly feasible for people who work on state trackers to release new versions of the API on top of the already existing drivers. There's no need to release the entire stack. The only portion that has to be deployed is the state tracker side. And that clear distinction between driver and API gives us the ability to distinguish between device driver bugs and the API level bugs. So the bugs that pertain to GL state tracking can be completely handled separately from the bugs that actually pertain to the hardware driver, which again makes development process a lot easier, allows splitting of the team between different sides, and allows people to actually find their interest. So someone who's interested in GL doesn't have to anymore figure out how the ATI chips work or how the Intel chips work, which is probably more true for open source, but certainly for the QA folks at different companies is going to be just as important. And how do state trackers really work? And how do we implement one? The simplest way to start is first figure out the API that you want to accelerate, be it a standard or a completely custom API. If you have a favorite general processing on GPU API and you wanted to figure out a way of actually implementing it on top of real GPUs, then Gallium is a wonderful solution for that. You come up with the API, and what do? You just stub it out, or at least that's the easiest way of actually starting with it. You stub out the entire API and just link it to the Gallium hardware driver and ONSYS to create some sort of a library. Then you proceed to create a very trivial example and link it to the library that you created in the previous step. And once that works, you have the setup. The setup is complete, and now it's really about implementing the stubs, which, as we know, is always very trivial. So what you really do is there's not a whole lot of researching that has to be done in terms of the Gallium API. Obviously, there's certain functions of different APIs that might be difficult to implement, at least semantically, on the 3D hardware. And at that point, if there's anything that the Gallium hardware interface is missing, then of course something has to be done. But in general, it's really trivial. It's just about stubbing out the API and then starting very simply from the bottom, implementing whatever the simplest functionality is possible, and just building it from there. All the state trackers that we have written, besides GL, which already had all the code, I think, written, were essentially done like that, and it certainly has been my approach. So you start usually with just clears and then move on from there. So just quickly to summarize before Brian and I go into state trackers. They're really used to implement APIs, and there's nothing more to it. Whatever API you're trying to support or whatever API you're trying to accelerate, that's really where the complexity will lie in the state trackers. And they do allow us to quickly adapt to new versions of standards, to new releases of different APIs, and very quickly provide them to the users. And because of the Gallium architecture, it means that if company A produces a state tracker for API B and releases it, then it's available to all hardware vendors who provide a Gallium driver at the same time, which brings that open source nature of the entire stack to everyone, and that sharing makes it possible to actually to not only share the knowledge but share the code in the form of state trackers. And they do make deployment a lot simpler by decoupling the device driver from the actual state handling. It's possible to release to make dedicated releases of just the device driver or just the state tracker, meaning that it's possible to fix bugs that actually relate only to the device driver or just to the state API separately, which makes it a lot easier. And something that is not mentioned here is, of course, that any fixes to the device driver profit all the APIs. And that's just GL that will profit from fixes in the device driver or the Gallium hardware driver. It's the OpenVG and OpenCL and XOR State Tracker. All of them will automatically profit, and optimizations in the device drivers will affect all the state trackers at the same time. So optimizations that were done thanks to the GL benchmarks will speed up our OpenVG implementation and will speed up our OpenCL and XOR State Trackers as well, which opens this new door in which you can use benchmarks for one API to speed up completely different API. And questions? I didn't have any. Again, besides the capital of France. I'm going to punt on that one. Anything? I guess Brian, it's you.
You would say one thing about you can implement the state tracker depending on the particular link system you have.
Right.
What would cause you to be able to or not be able to use a particular link?
So the WinSys is effectively, WinSys has a set of its own state trackers, really. It's the GLX state trackers, WGL state trackers. Those are the ones that actually connect to the WinSys. And basically every API has a way you create the actual context. For OpenVG and OpenGLES, that's going to be EGL. So depending on which kind of the WinSys state tracker you will link in. So you can, right now OpenVG is linked with the EGL state tracker, and EGL is used to create the context. But it will be perfectly feasible for someone to create an actual WGL, a wiggle, or really any kind of state tracker that is actually used to create OpenVG context. So it would be perfectly feasible to use any of the Windows APIs or add something to XLib to actually make it possible to directly create an OpenVG state tracker versus right now doing it with EGL. So it's like the diagram that Keith had, where he's had the GLX and DRI on one side and OpenGL on the other. The mixing of those two pieces makes it really possible to take the state tracker, the Gallium hardware driver state tracker, and mix it with any operating system / WinSys combination. I'm not sure. Does that answer your question?
Part of the problem is that we've got this component down the bottom called WinSys, which is for historic reasons, but you have the Windows system binding API out here, which has a very similar name.
Yeah.
Unfortunately. This name of the one down the bottom is kind of stuck, and it's kind of hard to get away from it. But there is, ideally, now that we have this second state tracker at the top, the Windows system binding state tracker shortens naturally the WinSys, but the name's already taken, so we can really do.
So the WinSys layer is not the Windows system binding.
Not really.
No.
Yeah. There is some tiny little bit of communication between the two to in small details to do with shared buffers and things like that, and getting text different map handles from the X server through the kernel, those types of things. But yeah, not really.
Yeah.
Are there other APIs on the horizon? I mean, this is supposed to be one of the benefits of this architecture. I mean, is there more APIs that you see coming?
OpenCL is coming. So basically, we're looking at all the Kronos APIs. We would like to support all of them. OpenCL is a more near-term plan than anything else right now. But I mean, there's XOR-StateTracker, which will be released very soon as well. So it's besides, we do have Direct3D state trackers as well, but the release plans for those, I think, missing in action, and I don't think actually we'll be releasing those anytime soon. The Direct3D. But all the Kronos APIs ideally should be supported, plus the XOR-StateTracker, of course. Yes?
Well, but GUI libraries, say, like Qt, for example, would make more sense to hardware accelerate Qt using OpenGL or OpenGLES or directly this Gallium?
This might go against what really today is about. But I think for those high-level projects, it makes more sense to accelerate using Kronos APIs versus the very low-level API of Gallium. Of course, there would be benefits to doing it that way. Unfortunately, the Gallium API is the Gallium hardware interface requires these complexity to be placed in the state trackers. So it would be a fair amount of work to actually implement the either Qt or Kairos API on top of the Gallium interface. The benefits that performance benefits that one would surely get due to the state handling that Gallium offers and the direct access to the hardware would be rather minimal, because it's for all of those vector graphics APIs. The complexity is in the actual path rendering and general font rendering versus state handling. So I think for 2D graphics APIs like Qt and Cairo, which already do have GL backends, there's probably a little benefit in implementing them on top of Gallium.
The functionality of the WinSys, it's like the functionality of EGL is a good example of what WinSys is expected to do.
Right. That top level WinSys.
Buffers are available with which kind of attributes, and then select one of them.
Right. That's the top level. Right. The top level WinSys would be responsible. So in the Qt world, that would be basically the Qt windowing system kind of a thing, and that would be basically responsible for it's everything that's required to set up a context for a given API. So the selection of the visuals and selection of the frame buffer formats, those probably should be done all in that high up WinSys level.
We need to rename something.
I know, right? It's the high WinSys, low WinSys.
Really a state tracker question necessarily, but as you get to
Not necessarily. What we've been advising lately is essentially creation of other interfaces. So we don't have a presentation on video, but this would certainly tie in with OpenMax. Essentially, what is happening is that instead of making this tiny Gallium interface really huge to encapsulate all of the functionality that can be possibly put in the hardware, what you do is create a smaller interface that, for example, in the OpenVG case, that would be just a path rendering interface. For video, that would be decode and encode the given frame and display the given frame. And that thin interface is then implemented by default on top of the Gallium interface. So the pipe context is used to give the default implementation of a given interface on top of the 3D hardware. And then the state tracker, which uses the given functionality, uses the new interface. And then the Gallium hardware driver, which is provided for a given GPU, if it does provide that functionality, so either path rendering or the video encode decode acceleration on a separate piece of silicon, either implements that interface or leaves it as is. Then the state tracker automatically picks it up. So depending on whether the hardware supports it, hardware can implement the given interface or not. And if it doesn't, then we'll go through the main pipe context interface and be implemented on top of the typical 3D hardware.
Where that gets interesting is the resource sharing question, because more and more of the front-end APIs, even such as current ones as OpenMax and GL, are having some ability to share data structures. And they're going through two different interfaces to get to the hardware. Is there a shared resource manager thing to do?
There is a shared buffer manager in Gallium, and in general, buffers are left up to Winces to decide what they actually are. For Gallium, they're very thin handles, and then the Winces actually figures out what does that handle actually mean, and what it actually is.
I guess I'd say at the top level as well, the pipe screen thing. At the top level, the pipe screen thing is the sharing, the surface sharing domain. And if these are if these shared objects are visible at the state track level, at the surface of the Gallium interface, then they would be managed by the pipe screen.
Right. So the screen is essentially the manager for all of them.